what you see here is our translation of a trivial 4x4 matrix from bits into atoms. And it is matrices like this that run AI models in general, from LeNet all the way to GPT. The thing that still fascinates me is how little is going on underneath. You take a matrix, you multiply it by another matrix, and you pass the result through a simple nonlinear function. That is more or less the whole vocabulary. You repeat that operation at enormous scale across rows and columns of numbers, and somewhere in the stacking of it, behavior we are willing to call intelligence begins to appear. To set some context, AI research today tends to take a common form. You have a dataset, you describe the network architecture, you state the loss function and the optimization, and you report the classification error rates over the training and test sets. What you are reading here is a verbatim quote from Karpathy's 2022 blog post, where he reproduces Jan LeCun's 1989 paper. His point is that the shape of the AI work has barely changed in over 3 decades from LeNet-1. So we dug deeper and we found footage of Jan LeCun himself demonstrating LeNet-1 at Bell Labs, which to me is one of the iconic moments in the history of AI. The piece on the right is the neocognitron from 1980. It is worth putting the two side by side because they answer different halves of the same problem. Fukushima gave us the architecture, a layered hierarchy with local receptor fields, whereas LeCun gave us the means to learn it by training that architecture with backpropagation. Today in 2026, almost 3 decades on, we have a whole zoo of architectures. AlexNet, ResNet, LSTMs, transformers, GANs, and so on. LeNet-1 is no longer used in practice, but it was the prototype that worked. It learned to recognize handwritten zip codes from real USPS mail, and the line of research it began was deployed commercially, reading handwritten checks at scale by the end of the 1990s. Set against the pace of the field now, LeNet-1 feels almost ancient. It has become a historical object rather than something of practical value. And that is exactly why it became interesting to us. We wanted to make a specimen of it. That is where the name artefact comes from. When we walk through a computer museum, we can stand in front of a different computing artifact, like the ones you see on the screen. And I think we have reached the point where it is no longer strange to stand in front of LeNet-1 in the same way as one of the foundational architectures of AI. For the few minutes I have left, I would like to briefly walk through the maker/artistic journey of building LeNet-1. I go much deeper on the motivation and on what the piece means in my interview with Luba, which is a better articulation that I can manage from this stage, so I would point you there afterwards. These are some of the early experiments for a single 4x4 module, working out how to route power and data through the grid. Note that we have made each module a 4x4 LEDs because the smallest pooling unit of the LeNet-1 is 4x4. This is the screen recording of Alex designing the PCB, and all of it were drawn by hand. And this is the final design we settled on. Next, neuron activation experiments. First test, driving a single layer of LEDs cleanly. Then 4 modules together off a Raspberry Pi to check the wiring scales. And here we fire the layers in sequence so that in the future we can show the forward propagation. We initially thought of providing each neuron a body, capsulating with each of these cubes. The cubes allowed diffusion of the lights, but for the final version of LeNet-1, we decided not to capsulate it. Before committing to glass and aluminum, we hung 1-to-1 paper prints to feel the real size and spacing in a room. This is the architecture we set out to physicalize. Everything you will see in LeNet-1 is a translation of this one diagram. Our first idea was to set each layer in epoxy. It failed twice over though. It trapped the heat from the LEDs and we could not cure it clear and bubble-free. So we used low iron tempered glass instead of epoxy. We use low iron because it is more transparent than normal glasses. Each layer is 2 glass panels held in aluminum extrusion. This is the final renders, 2 glass panels per layer, suspended in sequence. Then the fun part, cutting, crimping, wiring, and a great deal of assembling, mostly on a balcony in Seoul. And this is it, LeNet-1 running. This is the final form of the LeNet-1.